So now we'll get into a little bit of assembly. So you're probably familiar with push and pop, hopefully, with from x86, where you can actually push is doing a stack operation, which is a first in, last out, last in, first out. And you're going to have the element, the register that you're working with, put on the stack. And it's actually, these operations use the stack pointer, which was R13 that we saw earlier. So it's going to take the address that's in the stack pointer. So here's the example. So if we have the push R7 and link register, it will actually, and the stack pointer is here, if you notice, it's hex 7E-FFFF958. It's going to put the, and the stack actually on ARM here grows to lower memory addresses, just like in x86. So you're going to have the first element be put on the next 4 bytes, so that it's not going to modify the value at the stack pointer address. It's going to go 4 bytes up and write the value in the next 4 bytes, and then followed by 7E-FF950, which is the last element. So R7 gets put into 7E-FFF954, and link register, in this case, which is hex 8010, gets put into 7E-FFF, or FF950, right? So this is just a push operation. The stack is actually something that grows towards lower memory addresses. It's just a region in memory where you can store variables and things like that. So we'll get into more detail on that later. Pop actually works the same way, but in reverse. So it pops off the value first at the highest memory address back into a register, and same thing with the next element. So it just goes in reverse order and pops the elements back into the registers. So I'd mentioned before that ARM is using a load store architecture, so you're going to have to load from memory into the registers, and push and pop is one way of doing it. The arithmetic operations, just like in x86, you have simple add, where it takes the source register value, adds it to either an immediate value, which is any integer, or a value in the register. Add with carry actually sets the carry flag when you add. So if there's a carry that's generated when you add 2 register values, it sets the C flag in the CPSR. Subtract and subtract with carry work similarly. And reverse subtract actually reverses the operands for doing the subtraction. And reverse subtract with carry does the same thing, but with the carry flag set. I've actually put examples in the emulator. I'll talk a little bit about getting into the emulator a little bit later. Not all of the examples that you see in the slides are going to be in there, but most of them you can actually take this C code, put it into any of the other examples that are there, compile it using the make file, and you should be able to generate the assembly. So one of the examples here I have is a main function. It takes A, B, and adds them together. So if you actually look at the output that's generated by the assembler, you'll see that this is at no optimization. I've set the GCC optimization to 0. So it actually generates a lot of code, and you'll see that, actually let me show it. So if you want to start up the emulator, you can, and feel free to browse around on the emulator. So if you go to your home directory, go to projects, and then Linaro. And then if you just say start sim, it'll start up the simulator. So Linaro is actually an organization that's actually has several companies involved in open source development for the ARM platform. So ARM is actually part of it. So is Texas Instruments and all these vendors that are trying to come up with more open source development on the ARM platform. So they've actually built these Linux images. They have Android images for you to run. Their website is linaro.org. So this is what I'm using here for the emulation. So in your root directory, actually, you'll have a directory called projects. So if you look /root/projects, and all the examples are located up in the examples directory. Well, most of them. So to actually be able to run this, you run the make command. So once you've run make, you'll get an executable. And you can just say, you can execute the program by just saying /. So right now, example 1 doesn't output anything to the screen, but fortunately, the only editors that are available to you is Vim, because Emacs is way too slow. So actually, in the actual directory, you'll find the optimization level is not set to the one I have up here. So that's one difference to note. But what you'll see, what I just want to highlight here is the add instruction that we just looked at. So there's actually, you'll see there's an add with an S suffix at the bottom. And all that means is it's updating the flags in the CPSR. The special instruction that you also see is CP16, or I mean sub SP followed by 16. So this is a special form of the subtract instruction. And what that's saying is take the stack pointer, subtract 16, and store that back into the stack pointer. So generally, you would have subtract stack pointer, comma, stack pointer, comma, 16 to say, take the stack pointer, subtract 16, and then store it into the destination register, which is also the stack pointer. But this is sort of a shorthand notation. And as you can see here, the encoding for these are actually the opcodes that are generated by the compiler. So up here you'll see there's 32-bit instructions mixed with 16-bit instructions. So this is still in thumb mode, but it's using the unified assembly language. So I wanted to add an example for the subtract and reverse subtract, or subtract with carry and reverse subtract operations. So here in this example, I have hex A and R0 for both. This is sort of before the operation below and after the operation. So you start off with 0A, 0B, 0C, 0D, and when you do a reverse subtract, you're going to get a value that's really in the high range, but can anybody tell me which bit might be set in the flags after this operation?
Negative.
Yep. And? So the carry flag is going to be set. So
which one are we looking at? Are we looking at SBC?
SBC.
Okay.
Sorry. Yeah, so we're looking at the SBC instruction. We have 0A, 0B, 0C, 0D, and then we subtract A. We're essentially doing hex A minus 0A, 0B, 0C, 0D. Right?
So no overflow.
What's that?
No overflow?
No overflow, right. So there's going to be no overflow. You're not going to get a integer that's past the min, limit. So you're actually going to get the negative and the carry flags as Nick here said. So, and you're not going to generate an overflow. And the reverse subtract. I'm sorry. So in the subtract with carry, you're actually going to subtract A from A, B, C, D. Right? So this should be wrong. So you're going to have R0 minus R1, and then it's going to be stored in R0. And reverse subtract is going to be the other way, where you're going to take R1, subtract R0 from it, and then store it in R0. So these instructions are confusing, which is why I wanted to highlight it up here. So does that make sense?
Why is the carry set?
What's that?
For the reverse subtract, why is the carry flag set after?
The carry flag should not be set. And actually, in this example, one of the things, the CPSR, you're not going to see is accurate because the emulator is not accurate. So this is sort of what you're going to see on the emulator.
Okay.
But yeah, because when you access the CPSR, the flags aren't exactly correct. So I just wanted to point that out. Thank you, Gail. So this is what you're going to see on the emulator, but if you access the CPSR on the real hardware platform, you would see that the negative and the carry flags would be set. So for subtract with C. So the next thing we'll go into is the multiply operations. So multiply, it takes two registers, multiplies them, and stores it into the destination register. Then there's something called multiply with add, where it takes three registers actually, along with the destination, where it multiplies the first two and adds the third one and stores it into the destination register. So the register 3, which is referred to in the manual as RA, is actually called an addend, and it's the addition operand. Yes. And multiply with subtract is MLS, and it takes the first two registers, multiplies them, and then subtracts it from the third one.
Can you give any insight into why they provide these double operation?
I think it was meant for optimization for their hardware. So the instruction sets are generally based on their hardware design. So each architecture version, you'll see things, and they try to maintain backward compatibility. So I'm guessing this was a lot more for backward compatibility.
It was useful at some point in the past.
Yes.
With a lot of weird arithmetic instructions that seem to combine operation. It just didn't feel very risky. It felt like the opposite of that.
Right. That's true. So the other note that's interesting about these operations is the result is not dependent on whether the source is signed or not. So they'll just multiply and do the subtraction appropriately, and you'll get a signed or an unsigned value as a result. So here's an example. So I actually had to try to generate these instructions from the assembler. I actually put some effort. So if you just have the, generally ARM or GCC will actually optimize it such that if you're just using constant like these, it'll just output the value that's the result. So it'll actually do the calculation for you. And so, but this is what it would look like, right? If you had a multiply instruction and you used, so here it's going to multiply R0 and R1 and store the result in R0. And here it's going to take R1 and R0, multiply them, add R2, and store that result in R0. And Yep. So here was an actual example. So if you have R0 has, again, the famous hex value A, and R1 has the hex value E, you're going to get 8F in R0 after the multiply and add. So it's actually multiplying A and E, adding the value 3 to it, and you get 8F. And multiply with subtract is the same thing. Now, the confusing thing here is, I told you guys that the S suffix causes the flags to be updated. But here, the S actually means subtract, and does not mean, update the flag. So just be aware of that.
I have a question I might have missed. You mentioned something previous example. You have this mul.w.
Yes, thank you for highlighting that. So this is actually an artifact of GNU, the assembler. It uses it to tell the linker and everything to say, to tell it to basically use it as a wide. W stands for wide. The opposite of W is N, which is narrow. And it tells it to force the emulator to use 32-bit width sizes as opposed to 16-bit width sizes. So it's just an artifact. When you write the assembly program, you don't write that in. It's something that GNU does for the ARM emulator. So yeah, it's not really, doesn't mean anything. Now the interesting thing is, now we've done add, subtract, multiply. So there's obviously division, but there isn't. So on the Cortex-A profile, there is no integer division operation. It's all implemented using software. And the book I told you guys about actually has the algorithm that does the software-based division using all the other operations. So the only place where this is applicable is on the Cortex-R profile processors, which is meant for real-time embedded systems. They actually have a division operation, the SDiv and the signed divide and the unsigned divide. So on the Cortex-A profile, there is no division. So here again, I generated this by writing assembly. But this is what it might look like on the Cortex-R profile. Right? So you're going to have signed divide. It's going to take R0 divide by R1, store it into R0 for both cases. Now we actually, I have the instructions for running the emulator, but you can go in and actually see what the divide looks like on ARM using software emulation. So another note is, I know I said you can use SCP to copy files back and forth from the emulator for the work you've done, but there's another way. You can use Ubuntu's shared network folders to actually connect and copy stuff graphically if you want to. So I'll just show that to you guys now. So once you've started the emulator, right, so Control L will actually clear the screen if you don't like things getting lost at the bottom. But you can go to Places and hit Network. Connect to servers. So you go to Places, Connect to Server, and you pick SSH and localhost port 2200. You can just share the root folder. Username is ARM. And the password is password with a 0, just like for the VM, it's the same. So the port should be 2200. Oh, I know what the problem is. Sorry. So the username is actually root, not harm. So the port is 2200, and folder is just there we go. So you should have access to your directory and projects. And so all the labs that are in here and your examples are going to be in here. So you could actually edit using gedit or whatever you want if you like. It's compared to Vim on the emulator. So let me just introduce Object Dump real quick. So Object Dump is a utility that you can use to output the executable linkable format files. So whatever the executable that you generate is using the ELF format in the emulator. So you can actually dump it gives you the ARM assembly as well as the opcodes that are in the executable. So they're generally in a form that's before the link stage, essentially. So the linker actually takes static objects, dynamic objects, puts them together, but the ELF actually gives it to you before they're linked. So the addresses that you see might be different when actually run in memory. So the -G GDB option actually so the -G GDB option is used with GCC for embedding debug symbols into your executable. So Object Dump actually uses these symbols that are in the executable to show you in a nice format. So things like function names, variable names all show up. And so when you use Object Dump, you use the -D option, and finally you provide it the executable file, and it outputs all the assembly and opcodes for you. So here's an example. So this was Hello World. You can see it's using libc libraries to do the actual printf when you go into the example, but it's using offset tables and things like that. But it stores the string in a section of read-only data memory, and you can actually see the address and the actual values. So you just say object dump -d hello world, which is the executable, and I used pipeless to actually show me just a few snippets at a time. So now we can try dividing on the emulator. So if you go to projects and examples, and copy example 1 into a folder called div example, or you can just modify example 1 itself. This is just the add function. So that way you don't have to change the make file. And instead of doing an add, replace, instead of a plus b, return a divided by b. And then use object dump to see what code is generated for the divide. I'm going to try it out here. So if you want to remove the executable and objects, you can give an option to make called clobber. And make clobber will remove the object files, the .o files that are generated by GCC, as well as the executable. Make clean will only remove the object files and leave the executable alone. So these are just some of the options in your make file. So now if I say make, and then I run object dump -d example 1. So if you see here, so right here, this is our add function, and you can see that it's making a call to AEBI divide, IDIV, integer division. And if you look at that function, it's actually branching to integer division. And if you look at that function, it's actually branching to div si3 skip div 0. And then if you look at that guy, it's generating this long piece of code. You see a lot of you see a sort of pattern here. What it's doing is, Dave pointed this out, Dave Kepler, was that it's doing loop unrolling. So you'll see a lot of the same instructions were being repeated, but actually here, you can see it's doing a lot of left shifts, subtracts, and then compare. So this is what the divide function looks like on your Cortex-A profile. So, and believe it or not, I found out that they actually use this as a benchmark for the iPhone, for example. So see how long it takes for it to do a division operation. So a lot of the algorithm details are actually found in the book that I referenced earlier. So if you're interested, go check it out. So next I'll briefly go into the NOP instruction. So just like on x86, a NOP is an instruction that does nothing. But considering that it does nothing, it actually is used for code padding. So it doesn't add or remove from the execution time because it's optimized, and the ARM pipeline actually takes NOPs into consideration for either for skipping over or whatever. So you'll see that even though it does nothing, it's used quite often for alignment purposes and things like that. So it's also used for interrupt vector tables, which I'll go into more when we cover interrupts. And in some microcontrollers, it's also used for synchronizing the pipeline. So the next feature I'll talk about is the barrel shifter. So it's a hardware implemented multiplier/divider that actually multiplies and divides by power of 2. It essentially shifts your bits either left or right. And there's actually several instructions that allow you to do this in line with another instruction. So say you wanted to add 2 numbers, but you wanted to add one of the operands multiplied by 2 or power of 2, right? So you would use something like an arithmetic shift right, where you take the most significant bit, it shifts the bits by to the right by the specified number of bits. You actually specify an immediate value with the ASR instruction, and it shifts those bits by that much. And therefore, you're either multiplying by a power of 2 in this case. You can also shift left, right? And actually, sorry. So the arithmetic shift right is actually dividing by 2. The logical shift left is multiplying by 2. You're shifting bits to the right. So, shifting bits to the left. So logical shift right. The differences here are the way the carry bit is used. So the arithmetic shift right will actually take the rightmost bit that pops off the end and puts it into the carry bit. The logical shift left bit goes into the carry. The only interesting one here is the RRX instruction, which actually uses the carry bit to extend into the register value. So compared to the other ones, you won't have the carry bit being used to go into the register, So arithmetic shift right will take the value of the least significant bit, put it into the carry bit, but for RRX, it takes the carry bit and actually puts it into the register on the left. We'll see examples of this. So for example, right, the move R7, R5 with logical shift left 2. So what this is doing is it's taking the value in R5, multiplying by 2 to the power of 2, which is 4, and then putting that value into R7. Similarly, add R0, R1, R1, left shift, logical shift left by 1 is multiplying the value in R1 by 2, and then adding it to R1, and then storing the result in R0. So the only interesting thing, again, to repeat, is RRX takes the carry bit in, and since it's shifting right, it's going to move the carry bit into the most significant bit position, compared to the other ones, which actually just take the bits that are popped off and put that into the carry bit. So it allows you to do these sort of operations and in line with the instruction. So it's actually used as an optimization, where if you have to take an operand or some instruction and manipulate it in some way before you use it, this is the way to do it. So this is where I actually talk about the .w that was asked by Steve, I believe. And so it's, again, just a GNU assembler artifact. Even though the manual also uses it, it's basically the assembler is telling the ARM chip that's executing which encoding to use. The narrow is for 16-bit encoding, W is for 32-bit encoding. Again, to recap, S means update the flags in the CPSR unless it's MLS or specific instructions that don't use S that way. And so I just want to emphasize, we don't use the .n or the .w in our assembly code. It's generated by GNU assembler. So an example for the barrel shifter. So if you're doing a multiply by 2 function, where all you're doing is multiplying by 2, so it will actually take that function and generate a logical shift left and update the flags. So here you can see R0 is being multiplied by 2 and then stored in R0. So if you do multiply and add by 2, which is also in multiply and add by 2, which is using the add instruction that I covered earlier, it will take R1, multiply by 2, add to R0, and then store it into R0. This one is actually a divide by 2 example. This one is interesting in that when I wrote the code to divide by 2, it generated an add and an arithmetic shift right. operation. So it's actually doing a divide by 2, but if you see, it's taking R0 and taking this, it's essentially trying to get the sign bit. So it's trying to get the sign bit so it can set the flag for negative. So it's shifting the entire value by 31 bits, setting the flag because the arithmetic shift right is actually using 2's complement notation. So the S flag on the ASRS is actually updating the flag. So that's how divide by 2 works. So this actually example is in your examples directory if you want to try it out.
In example 3.2c,
Yep.
why do you have to, in the divide by 2 function, what does the add do for you? Other than getting a bit.
Yeah. So
what's the purpose of that?
So the add is actually, if you look, it's actually taking R0, shifting right by 31 bits. So it gets you that last bit, essentially.
Okay.
Okay. And then okay, so this is the 2's complement notation for -8. So with this, sorry, it's right here. So what it's going to do is it's going to take FF8 down here. It's going to shift that to the right. So you're going to get all zeros, right, except for 1 in the least significant bit position. Then it's going to add it to the value in there already, so you're going to get FFFF9, right? So this one's actually going to give you -7, I believe. And so now what happens is, so you've gone from -8 to -7, right? And then you shift right by 1. What happens is you're taking -7 and essentially dividing it by 2, but you're still keeping the negative bit intact. So you're going to get -4 here. So when you divide -8 by 2, you're actually taking that negative into account. Does that make sense? It's a 2's complement divide. So, okay. So this is for rotate right with extend and the logical shift left. So down below, I'm following the same convention here, which is below is before the operation and above is after the operation. And the red values indicate the values that have changed. So when you do a rotate right with extend, and you can see here there's no immediate value being specified. So the default here is 1. So it takes the value, rotates right by 1 bit, and since you're doing a move negative, it's actually taking the complement of the value in R0 and then shifting it by 1 and storing it into R0. So this is a more sort of complex example of how RRX works. And logical shift left, you've already seen, it's multiplying by 2 to the power of 4, and then adding it to the value in R0 and storing it in R0. So